And yesterday I posted the rest of everything that I'm going to post this semester. So lecture 6, example 6, the last formative assessment, and the last homework. Everything is available to you. So if you want to speed your way through it and be done, I'm fine with that. If you want to stay on the pace of the class, I'm fine with that too. Whatever works best for you guys is what works best for me. I did not change much, if anything, from what it was last year. So the videos covering from last semester should hold for most of it. I changed a little bit in homework 4. That's the only thing that I can think of that would change your strategy for how to code things and such. But so let's see, where are we at today? We are at April Fool's Day. So that means the next thing that you have a formative assessment due on Tuesday. No fooling. For real, it's due. And it should help you get started with homework 4 if you haven't gotten started with that already, which will be the next thing after that. So, any homework questions, logistics questions, anything like that that we need to talk about to start the show? No, we're good? Good, quiet. All right. Fine by me. Then let's see here. Last time we started talking about transitioning from an example of how to fit categorical grouping variables as predictors and transitioning into how to fit nonlinear trends for quantitative predictors. So I wanted to start with that as a more general topic. So I am on slide 23 of lecture 4, nonlinear trends. So I'll show you a couple different variants on this. So when we talked about Pearson correlation as a measure of bivariate association, one of the things that I wanted to emphasize was that Pearson correlation measures a very particular kind of association, a linear association. As x goes up, y goes up. As x goes up, y goes down, that kind of thing. But there's a lot of quantitative variables that are likely to have nonlinear relationships with an outcome. And so I wanted to give you some tools as to how you can specify and test those types of nonlinear relationships as well. So this is the kind of topic that doesn't normally get included in an introductory stats course. I have chosen to include it because I think it's important. I think it's something that people don't necessarily appreciate until they're faced with models for change over time, for instance, in which this comes up. So I'm actually talking about this right now in the longitudinal class that meets after this one. I want you to have this set of skills to model nonlinear trends of any kind of quantitative predictor, not just time. So age is the example that we have here, as well as education, because a 1 unit change in education does not buy you the same change in predicted income. So that was sort of a silly model for us to have fit initially. We'll make a better model today. Maybe next time. We'll see how far we get. So 3 different examples that I want to show you in this unit. Curvilinear effects. So we can combine what's known as linear and quadratic slopes. So if you put in a predictor that's quantitative and you fit a slope to it, that's a linear slope. You can take that predictor and square it, and the slope that is applied to that squared predictor is known as a quadratic slope. So that's what we had started talking about last time. And those combine to create a U-shaped curve. Another option for creating a curvilinear effect is to log transform your predictor. So do you remember that from maybe like a month ago, 2 months ago? Log transforming was an example of a nonlinear transformation. In this case, the objective of the transformation would be to create a regression line that looks more like an exponential curve. So a line where as x goes up, y stops going up to the same extent. So log transforming a predictor is like a cheap and dirty way of getting that exponential curve that you would normally need a truly nonlinear model for. The advantage of doing it this way is that you can use standard software. And you're frozen, which means I'm frozen.
Okay, is she frozen or am I frozen?
We're all frozen. Am I back? Now we're back. I get the dreaded unstable message. I'm the only one here in the house today, so no one else is hogging my internet, and I have every other program shut off that would possibly use it, so this is as good as it gets. However, there are 2 different roofs being torn off the house next door is getting a new roof and the house across the street is getting a new roof. So possibly there's some power issues with that. I don't know, but we'll see. All right, but we're back. We're back. Yes? That was not rhetorical. Okay, good. All right, so log transforming. Piecewise effects. So the idea that the effect of a quantitative predictor can be compartmentalized into different regions of the predictor having different effects. That's also known as linear splines, so or regression splines. You may have heard of this under that terminology. I'm going to teach you that too. And then last but not least, the idea of whether or not you can take an ordinal variable and pretend like it is interval and give it a linear slope. You can actually phrase that as a testable hypothesis, and so I want to teach you how to do that. So several different examples. And I think I asked you this before, but have you seen any of this in your previous coursework or research experiences? You're not sure if you've seen it? Is that what that means? Jen, have you seen it? Nope. I don't know. Is that surprised face? Is that what that emoji is?
Yeah, there's no thumbs down, so that's the closest that I can find.
Yeah, if I ran the Zoom, I would not only add thumbs down, I would add thumbs sideways for like, so. But okay, so good to know that we'll use the surprised faces as thumbs down. You can
So,
also use the chat window.
to reduce the variability in one of my, in my project, one statistician told me that I could use natural log transformation. So I did that
On a predictor or an outcome or both?
on the outcome.
On the outcome. Yeah, that is a different use of the same transformation. When you transform an outcome, it's usually to make it less positively skewed. To sort of it reels in the tail and it spreads out the lower end. So when you're transforming a predictor, it's not done with a concern about a distribution, because predictors can have whatever distribution. There's no assumptions on that. It's just changing the line that's created as a result. So, all right. So this is new stuff. So that's good news. So I'm earning my keep then, bringing you some new information today. So here's a little bit more about the first two we talked about, quadratic and exponential. So if what we've talked about thus far in terms of having a slope for a predictor is a linear slope specifically. So now we make a distinction as to what a linear slope tells you and what a quadratic slope tells you. So a regression model, a general linear model, that would be used to look at a quadratic effect of a predictor X, generally would look like this, where we would have beta 0, that is my fixed intercept. And vocabulary drill, what is a fixed intercept again? What does beta 0 tell me? I don't know if this is a gesture question or not, but you can make it one.
Well, I tried, but you are here, the intercept.
Yes, it is the you are here. I think Jen is doing where the clock crosses the y-axis. Is that what this is? Yep. Yep, it's the expected value of y when your predictors are 0. So as usual, we want to make sure that x has a meaningful 0 somewhere so that the you are here sign is actually in the data. We have x and we have x squared as two distinct predictors. And in order to create a quadratic trend, they both have to be there. So x squared is only interpretable as a quadratic trend if it's paired with x as the linear trend. Otherwise, x squared, the slope coefficient, will give you sort of a mishmash of the two. And exponential would look like this. Instead, where we would transform x ahead of time, we would make a new column for x that is the log transformed version, natural log by the way, and then the slope would become the effect of the change in y for a 1 unit change in log x. So with respect to the log, it's still a linear slope, but if you back translate that x out of the log, if you exponentiate it back to its original scale, then it creates a curve. And I've got a picture that will help explain that a little bit better. So the tricky part with quadratic slopes, this is, I think, something that is not commonly understood. A lot of people want to wave their hands and be like, oh, it's too complicated. I can't interpret the coefficients. No, it's not that complicated. Two. The answer is 2. The trick to interpreting a quadratic slope correctly is to multiply it by 2. Cough, cough, homework question. Cough, cough. Twice the quadratic slope is how the linear slope changes per unit of the predictor. So the whole idea of a quadratic model is that you are taking the slope of a predictor and you are either speeding it up or you are slowing it down. So if it's speeding up, that's known as acceleration, like in physics terms where you have velocity and acceleration, or deceleration if you're slowing it down. And twice the quadratic coefficient is how the slope either speeds up or slows down per unit of the predictor. I've got some pictures for you that will make that hopefully a little bit clearer. Why is it twice? I can give you, at this point in the course, I can only give you one real explanation. The answer is that we're actually talking about the second derivative of a function with respect to the predictor. So by the rules of differentiation, if you remember calculus from high school or whenever you would have had it, if I take the first derivative of this function with respect to x, then I bring the coefficient in front of it down, I bring the exponent down, and I multiply it. So the second derivative then is twice the quadratic coefficient. I don't expect you to necessarily care about any of that, just as long as you remember the rule that we have to multiply the quadratic coefficient by 2. So here's some pictures. In general, there's only 2 kinds of quadratics, right? There's either the upside down u or the right side up u. But the trick to interpreting how the quadratic and the linear terms work together is to figure out where on the u you are in addition to which kind of u it is. So there's really 4 possible combinations for what you would observe in your data with respect to the range of the predictor that's in your sample. You can either have a linear slope that gets sped up, so acceleration, it's a positive slope that gets more positive. That's this first picture here on the top left. You can have a positive slope that slows down. So that's the top picture here on the right, where we have a relationship. The relationship is diminishing the further up you go. You can have a negative slope that slows down. That's the bottom lower left here. Or you can have a negative slope that speeds up. And so I would classify the top left picture and the bottom right picture as acceleration, because in that section of the U, you are either speeding up your positive slope or you're speeding up your negative slope. Whereas the bottom left and the top right are deceleration pictures. You're taking a slope and you're reducing its impact the further up the variable that you go. And so the trick to knowing which of these you have is to look at the signs. So given the idea of a nonlinear slope here, we have to pay much more attention to how we interpret the slope coefficient of x to begin with. So going back to this regression model right here, I'm talking about the interpretation of beta 1. It is incorrect to say that this is the linear slope of x, because that explanation is not specific enough. So it is incorrect to say beta 1 is the change in y for a 1 unit change in x. You have to add to that phrase that beta 1 is the change in y for a 1 unit change in x at x equals 0 specifically. So that at x equals 0 part makes it conditional, because a function that has a curvature to it has a bunch of different linear slopes. So beta 1 in physics terms is giving you the slope of the line that's tangent to the function at that point. But the whole idea, I get my prop here, if I have a curve, is that the linear slope changes all along the curve. So beta 1 tells you one of the possible linear slopes, wherever 0 is. And the model allows you to predict what any of the other linear slopes would be as linear combinations. And just as we've done for linear combinations to get group means and group mean differences, we can use estimate statements in Sas or lincom statements in Stata to get any of that. So beta 1 is the linear slope of x specifically when x equals 0, because that's the only point here where beta 2 would drop out. Otherwise, the linear slope at any value of x is a function of both beta 1 and beta 2. So in the pictures, note that my x-axis here is time. I actually borrowed this picture from my longitudinal class. So if I have a variable x here, 0 is the first value that is observed. So 0 is my first occasion. 4 is the slope of this little dashed line right here at x equals 0, where x is time. So at time 0, there is a 4-unit change in y for a 1-unit change in time. As you move upward, for every increment in time, for a 1-unit change in x, that linear slope becomes more positive because the quadratic slope coefficient is a positive. It becomes more positive by twice the quadratic. So the slope at time 1, 1 unit later, is 4.6. The slope at time 2 is 5.2, and so on. So the difference in those subsequent linear slopes is twice the quadratic coefficient. Okay, how are we doing so far? Yeah, 2 thumbs. No thumbs from you, Jen, yet. You okay? Okay. Emmy, you okay?
Yeah, I'm a little upset high school calculus and physics were brought up without any warning, but otherwise I'm okay.
I've traumatized you.
Yeah, maybe a little bit.
I was just trying to say you've probably seen this before, and it may have been many years ago. Calculus was like, trying to do the math in my head. Calculus was 26 years ago for me, and I never took any advanced math in college beyond that. So I'm not saying that any of this is necessarily needs to be at the tip of your fingertips, so to speak, the top of your head. Just that these are ideas that you've probably had exposure to before. But if not, then all you need to know is twice. Twice the quadratic coefficient describes how it changes the linear slope coefficient per unit x. So it's a definitional thing at that point. So this one, it takes that positive linear slope and makes it more positive by twice the quadratic coefficient for each of these units. Top right over here, it takes the same positive slope of 4 at time 0, but it makes it less positive. So it decreases the linear slope by twice the quadratic coefficient because the coefficient itself is negative. And this picture, the top right and the bottom right are the same picture essentially. The top is the first part of it, and the bottom picture describes what would happen if we kept following it out. So the bottom one describes a negative slope that becomes more negative or stronger as time goes on, whereas then the bottom left is a negative slope that becomes less negative. So the bad thing about these models is that it is sometimes unrealistic to expect that what goes up must come back down, or that what goes down must come up, right? They're often used in a context in which you would expect that an effect would die off or sort of asymptote at some point where more doesn't help. But instead, these models actually predict that more would not only not help, but make things worse. So that can be somewhat theoretically disjointed with whatever phenomenon that you're looking at. But quadratics are good for relationships that are U-shaped. That's really what they're intended to describe. Like this one. So this is the example we started looking at last time, where we have chronological years of age measured in a sample from age 18 up to about 76. So I made this plot in Sas by first computing what the mean income is for every 2 years of age. So age is a continuous variable. In this case, it's measured to the nearest year, but I rounded it to 2 years just so that I could get a mean to make this picture with. And so this is probably the cleanest example of a quadratic U-shaped trend that I've ever seen in real data. and it's not that clean. But the shape of it is pretty much textbook quadratic, where income looks like it increases up to some point in middle age, at which point it starts to decrease as a function of age instead, albeit quite noisily, depending on with relatively few individuals at this side of the distribution. You can see that the standard error red bars get wider and wider as you get older and older. There's fewer cases on this edge. So I wanted to show you how to fit this type of pattern to age in Stata and Sas. So we looked at this last time. Step 1 is to center your predictor variable so that 0 is meaningful. So this is necessary not only for the "you are here" sign for the intercept to be meaningful, but also for the linear slope, because the linear slope of your predictor is going to be specifically when that predictor is 0. So you want to make sure that 0 is meaningful. In this example, I chose to center age at the minimum value, so we could talk about what happens as age increases relative to the sample minimum of 18 years. So I first created that new variable, and then to fit that quadratic U-shaped trend, I included the new centered version of age as well as its square. So in Sas, you can on the fly create a new variable that is a multiplicative combination of any two predictors or even 3 with this star. And you can do the same thing in Stata with this symbol right here, which we can decide. You all look a lot younger than me. Is this the hashtag? Hashtag or pound sign? To me, it's a pound sign. I'm not on the Twitter, but I've heard of it before. So star in Sas, hashtag in Stata to define interaction terms more generally, of which this squared version is just a special case. Okay. Questions or comments as I refuel here?
So in the Sas code, under model income equals age 18.
Mhm.
So we are the first part age 18, then we are multiplying that again with the quadratic version of it.
The quadratic version is age 18 squared. The predictor
Okay.
variable is the squared term.
And so what is the first age 18 doing?
It is the linear term.
Okay.
So the squared version is only the rate, it only describes purely acceleration or deceleration if it is above and beyond the linear slope.
So we have two columns here, right? One is the linear. Okay, makes sense.
Yep. So we have the original column, which is age. The first step here then is to make a new column in the data. So this is happening in a data step here in Sas, and for the generate option in Stata, a new column which is age minus 18. Then we don't actually have to create this squared column. It's being done for you as part of the model estimation. That's one of the nice things about the GLM procedures, is that you don't have to a priori physically make interaction terms as new variables, whereas you do in a lot of other packages. And it gets annoying to anticipate like every possible combination of squared terms or interaction terms you might want to test and have to make them as columns. So this is not making a new column, it's making a new column just within the context of the model. Okay, did that answer your question? Makes sense? Okay. All right, other questions on the codes? Okay, so this is as much as I am going to ask you to do for your homework. Fit a quadratic model, interpret the coefficients. I have some extra codes in the example that goes with this that we'll go over in just a second, but I wanted to make that point. I'm not asking you to do anything more complex than just fitting this model. And actually, the predictor variable in your homework is already such that 0 is near the mean, so I'm not even asking you to center it, just to fit the squared term of the predictor. So the only way to screw it up is to forget the linear one. That's really the only thing that you could do wrong. There are very few degrees of freedom on this. So here's the results from this analysis. I'll show you in just a moment. So we have beta 0. Beta 0, my fixed intercept, you are here sign, always the expected outcome when your predictors are 0. My predictors are 0 at age 18. So this idea of describing the centering constant explicitly in the equation, this is a good habit to get into, because then whoever's looking at your equation knows exactly what everything means. Whereas if you don't have the centering constant in here, they'd have to read your text to describe how each of the variables was coded. So by putting age 18 in here, that is telling my reader that beta 0 is going to be the expected outcome at age 18 specifically. So that was estimated at 2.6. So the average 18-year-old is predicted to make about $2,700. And that is not zero, so they do get to make some money. The linear age slope. So this is the tricky one. A slope is always the change in y for a 1 unit change in x. But because this is the slope of a predictor that is also involved in an interaction term, because there's age and age squared, it is insufficient to say that this is the effective age. It is the effective age when age is 0, specifically, because of the beta 2. So the way that you can interpret this is the instantaneous, as they say. This is a physics term that is borrowed in talking about these models. It is the instantaneous effective age at age 18, which is where 0 is. So at that point, for every year older you are, you're predicted to make about $1,200 more. So if you go back to the U-shaped curve that we have, it's the slope at the beginning of the curve is what we've just estimated. The slope at this point specifically. So that slope at age 18 is 1.2. The model is going to predict then that the slope is going to do what? Is it going to speed up or is it going to slow down? What does it look like is going to happen based on just staring at the data? The slope at age 18, is it going to speed up or slow down?
Speed up.
I'm gonna say slow down because it looks like it's less steep. It's
Yeah,
flatter.
it flattens out. This is a very messy trajectory. I'll show you what the model fitted one looks like in just a second. But it does slow down. It's this one right here. So that blue line is what the model is fitting. So note that the x-axis here is centered age, so 0 is where 18 is. So the slope that is tangent to this curve right here, that's 1.2. The model is predicting that that slope slows down, becomes less positive, or decelerates. You can pick your term. So it's not that age doesn't matter. It matters less and less as you go on. And at some point, the slope that would be implied by this curve is flat. And you can actually calculate the age at which that occurs, which I did. So the instantaneous slope of age at age 0 is 1.2, and that was significantly greater than 0, as indicated by my p-value. The quadratic slope then gives you half the rate of acceleration or deceleration, so you got to multiply it by 2. So minus 0.02 is my quadratic slope. That is also significantly different than 0, significantly negative. So what it's going to do is for every year older you are, the linear slope of age becomes less positive by 0.04. Twice the quadratic. The linear slope of age becomes less positive, starts out positive, becomes less positive by 0.04. So the model tells me via beta 1 what the linear slope is at age 0 specifically, but all of the others are linear combinations. So I can ask for predicted outcome values for any age, and I can ask for predicted linear slopes at any age as well. So filling in the values of these coefficients, the fixed intercept of 2.6 to create a predicted income, which is my outcome variable. At any age, I start with that. I fill in the sample estimate for beta 1 right here, multiplied by the value of centered age that I want the prediction for. So this line is predicting what income is at age 30. So I fill in a 12 here because relative to age 18, 30 is 12 more. So always make sure that you're filling in relative to the centered values when you make these predictions. And then the quadratic coefficient estimated by the model, beta 2, goes here, and age squared. So then Sas did the math for me, figured out that age 30, that income is predicted to be about $14,000. And at age 50, doing the same math, it's predicted to be $21,000. But at age 70, it's predicted to be back down to 13. So at some point, the positive slope of age hits 0 and switches directions. So if you're an older adult, the older you are, the less money you make. If you're a younger adult, the older you are, the more money you make. And here is a formula, by the way, at the bottom of this slide 29, by which you can find, I think it's called the aperture. Does that sound right? I'm pretty sure that's right. I might be saying it wrong, but it's the point where the curve hits a minimum or maximum value. And so it's actually calculated in this example as age 48. So age 48 is the point where the curve hits 0 and then switches to be negative instead. So do the predicted value parts make sense? Just filling in ages into my regression equation?
Dr. Hoffman, can you go over the why it's half the rate of acceleration one more time in the quadratic age slope?
To use the quadratic slope to describe how the linear slope changes, you have to multiply it by 2, because what is provided to you directly is half the rate of acceleration or deceleration. Not better yet?
Not quite.
Not
Still
quite.
a little confused.
So for a quadratic function, the linear slope at any point is actually the first derivative of the function, and the change in the linear slope across the function is the second derivative. And so by the rules of differentiation, that squared term, the 2 in the exponent, when you differentiate, comes down to the front and multiplies the coefficient that's there. So it's just a math thing. Twice the quadratic coefficient is how it changes the linear slope. It is what it is. I have another explanation that I can give you, but it works with interaction terms, and we haven't talked about those yet, so that probably won't help in this class. But I can re-give that explanation in a few weeks when we get there. So, twice. So these rows right here give me predicted income. These rows right here describe how the model predicts what the linear slope would be at any age. And it starts off with what the linear slope is at age 0, which is 18. And then you fill in the quadratic coefficient multiplied by 2 for the age you want the linear slope for. So at age 30, the slope for the effective age is still positive. So it was 1.2 at age 18. It becomes 0.75 at age 30. At age 50, it's negative. So 50 is past the flipping point. So it's going up. It's 0 when you hit age 48, and now it's turning negative. And then by the time you're at age 70, the slope is negative, and significantly so. So all in all, the dashed line through this mess here, that's what the model is predicting. So the maximum point of the function where the 0 slope of age would be observed is about age 48 right here. So just like we had two slopes that work together to describe the differences across three groups, this model requires two slopes to describe the effect of age. So anytime that you need to lump together slopes to be able to talk about their joint effect as answering a question, that's what our friend F is for. So in this model, I spent two slopes. I have 731 left that I could have spent. That got me an F value of 47. The residual variance for the amount of unexplained variance in income is 169. The p-value that corresponds to that F tells me that I would expect to see two slopes this strong or stronger if the population slopes were 0, less than 0.01% of the time. And last but not least, an R-square of 0.11 means that I have explained with these two slopes for age 11% of the total outcome variation. If I take this R-squared and find the square root, that gets me to this R right here, which is 0.34. And that describes how correlated y hat is based on this quadratic line with the real y hat, or the real y's, excuse me. So it's a correlation of 0.34, which is significantly greater than 0. So same idea in terms of lumping slopes together, but for a different reason. In this case, what this result right here is telling me is how well age relates to income. But to answer the question of how age relates to income, it takes two slopes to do it. It takes a linear slope of age paired with a quadratic slope of age. Okay, does that make it better? Ish. Big picture, the idea here is you need F anytime it takes more than one slope to describe the effect of a predictor. That's the big picture. So this is just another special case in which that would happen when you have linear and quadratic slopes instead of grouping variables, for instance. So questions? Any of that I can tell you again or try to do differently to make it better? Note I said try. I make no promises, but I can promise to try. Do you want to see the Sas code? Data code? Yeah, why not? Since you're going to have to practice it, it'd be good to get a chance with that. I am on, move this thing out of the way. I am on page 9 of example 4. So we had previously looked at linear effective age for these data and found that if I just put in age 18 by itself as a predictor, so going back to page 7 here just for a second, if I put in age 18 as a linear slope, then that slope accounted for 4% of the variance in income. So the extent of a linear relationship between age and income, what Pearson correlation would have told me, captured 4% of the variability in income. So 96% still out there. And if I only have one slope in the model, then the f-test for that one slope is telling me the exact same thing as the t-test for the slope. Do you remember the relationship between them? How are t and f related if I only have one slope in the model? Anybody remember?
T square is F.
Yes, it is. So if I have one slope in the model, the test of whether that slope is different than 0 via t is the exact same thing as asking whether the model significantly predicts outcome variance. So the test for significance of this R square, the model test, is the same thing as the t-test. This t squared is my f. Now if I add the squared term, so the model that we just looked at in the PowerPoint, picking up a beta 2 slope as the fixed slope for h squared, adding that into the model. These are the extra statements that I wanted to show you in your life, but that you do not need to do in your homework. Okay? I make the distinction, right? I try to give you ammunition by which to live your life, but I didn't want to require too much in one setting. And by the way, all of this code right here, this output out thing, you don't need that either. What that does though is save pieces of output either that are part of the results as tables or that I'm asking it to generate behind the scenes as Sas data sets. So what this line in particular is doing, output out, is building a new Sas data set that is called pred income by age, and it is going to have a column for the predicted outcome according to the model. So that's why I named it y hat age is what the column's going to be called. And I'm also asking for the standard error for that y hat for each person. So I'm building a new data set that has 2 more columns to it with y hat and the standard error of y hat. And that's how I made the pictures. So just, again, for life, resources that you can have, not something that I need you to do. This is the sort of thing that's automatically built into R, because when you save a model, you're saving all the pieces of stuff that went with the model, and then you can access it. In Sas and Stata, the saving doesn't happen automatically. You have to ask it to do that. But these estimate statements right here in Sas and these lincom statements in Stata are doing the same thing. Those are generating predicted outcomes for the specific ages that I requested. So I'm asking it to internally represent what beta 0 is going to be as the intercept, what beta 1 is going to be as the linear slope for age, multiplied by the centered value of age that I want the prediction for, and then what beta 2 is going to be by referencing the squared term, multiplied by age squared. And so that's how I got the predicted income at age 30, 50, and 70 by filling in those values as multipliers of the fixed effects estimated by the model. And then the linear slopes at each age function similarly, except that what I need is 1 beta 1, and then I need 2 times the value of age that I want the linear slope for. So that's how you can get what the slope is predicted to be at any point on the function, as well as its standard error and p-value. So that's the advantage of doing these sorts of commands over hand calculations. So in homework 4, for instance, there's several questions that you could do by yourself with a calculator. Like, what's the difference between this group, or what's the mean of this group? But to prevent you from only using a calculator, I also ask for their standard errors, because the program will give those to you. Technically speaking, you could get your calculator to give you standard errors as well, but it's much more painful. And I didn't give you the formulas on purpose, because I want you to make the program do all of the math for you. So linear combinations of model parameters is the overall concept here, hoping to demonstrate. All right, Fayaz, did you have a question? No, you're just leaning forward like you're hanging on my every word. Yeah, estimate statements are cool. I wish I had learned these so much earlier. By the time I learned these, I had come up with a million workarounds that were much more labor intensive and redundant. So here's my results. My new model has 2 slopes in it. Is my model R square significant? And I'm frozen again. Are we back? Now we're back. Okay. Yeah. So first question, is my model R square significant? Highlight that too. Thumbs up for significant, thumbs down for non. I got squinting and 1 thumb.
Which number are we looking at?
That's my question. Yes, this is an exercise in remembering where to look. Yeah, so my question is the model R square significant? So we got the majority rules says yes. And what did you look at to tell me that?
The p-value of the f.
Yeah, so this f right here is testing the joint contribution of the two slopes, the linear slope of age and the quadratic slope of age, and the p-value right here is my significance test for that f. So f tells me whether or not my model significantly predicts the outcome variable. The r square is the effect size for how well my model predicts the outcome variable. How well it predicts is quantified as proportion explained variance. So 11% explained variance. No?
I mean, it's not good. Like, it's really low, right?
Oh, in real data, this is about as good as it gets. Yeah, if you think this is bad, then you've been playing with textbook data where they make shit up and everything works perfectly. Yeah. Like in your homework, you're going to have like r squares of 80% in your homework because I made it up that way. But yeah, not in the data that I played with. This is a relatively good result. So here's a question for you. This f right here, we just agreed, is testing this r square against 0. So f of 47 is telling me whether 11% is greater than 0. Do you remember what the r square was in the previous model that only had linear age? No, that's okay if you don't remember. I just looked at it again, which is how I know the answer to this, because I knew I was going to ask this question. The previous r square for linear age only was 4%. Now, by adding quadratic age, I'm up to 11%. So a change of roughly 7%. Is there anything on this page that would tell me whether that change in r square of going from 4% to 11% is significant? Is there anything on my screen here that would answer that question? Now, I haven't taught you this yet directly, so I'm looking for an extrapolation or interpolation, whatever the word is. So the question is, I had an r square of 4% from linear age by itself. My r square went up from 4% to 11% by adding quadratic age. Is there anything on my screen that would tell me whether that change in r square itself is significant? I'll give you the answer. Yes, there is. Now, where is it? What is it? Any guesses?
Confidence interval?
Which one?
The 95% confidence limit.
I see
For the
3 of them.
intercept? For the intercept?
For the intercept, nope. Because
No.
the intercept was in the previous model also.
For the linear model?
The linear slope was also in the previous model.
Then
What's
it must be for
new?
the quadratic.
Yeah. So in this case, because the only thing that separates the previous linear age model from the current quadratic age model is the addition of this beta 2 term right here. This is what made the r square go up. It's the only thing that's different between the models. So if that slope for the incremental contribution of the quadratic effective age is significant, so is the change in r square that it caused. 1-to-1 correspondence in the same way that the f corresponds to the t if you only have one slope. So I'll say that again in total. Previous model that had just linear age in it, intercept plus linear age, explained 4% of the variance. I added this, that line. I added a beta 2 for the effective age squared. That's the only thing that makes the models different. Therefore, that line has to be responsible for the increase in R square up to 11%. So if the new slope that I added was significant, the change in R square that it created is also significant. 1-to-1 correspondence. Does that make sense? Maybe? Ish. Okay. So in the next unit, the only new concept, by the way, is how you answer this question if you add 2 or more slopes instead. And it is going to require 1 more line of code. But we're not going there yet. Just 1 line in this case. So if I added 1 slope to the model, the test of that 1 slope is the same test as to whether the R square increase that it generated is significant. So I know from this F that 11% is not 0. I know from this T that the change relative to the previous model is significant. All right, and another review. 2 different ways to interpret R square. R square is proportion reduction in the unexplained variance. So relative to the empty model, by what proportion did we reduce the residual variance? The other way to think about it is to unsquare it and talk about it as a correlation. If I do that, if I unsquare R square and put it back down to R, then it is the correlation between what and what? Not rhetorical. R is the correlation between what and what that would turn it into an R square. No
Age and
guesses?
income?
Income is one of them. Age is related to that, but not exactly right. So if it were age and income, then that would be describing a linear relationship. Do you want to try that again? Or phone a friend? You're very close. In this case, it is the income that is predicted by age, y hat. So if you unsquare that R square and put it back down into R, that tells you the correlation between y hat and y. So the income that was predicted by age, where the prediction takes into account both the linear slope and the quadratic slope. Okay. And here's the answers for the estimate statements. So this is where I got the predicted income at particular ages that I requested, as well as the predicted linear slopes at those ages as well. And that's what the model predicts. So I made this picture on the right by generating y hat and then asking for a plot of it. And all of the code to do that, by the way, is in the online files. I didn't bother to include it here, but you have it for your reference if you want to learn how to make plots. In terms of whether or not I should believe my model results, in particular the standard errors, looking at normality of the residuals as well as heteroscedasticity, constant, non-constant variance, looks like we might have a little bit of problem with that with respect to the latter. So there are ways to build non-constant variance for the residuals into your model, but not using ProcGLM. You can do that using something called ProcMixed, which is a separate class. So I can teach you that some other day. And as always, words. Because words matter. And apparently I can't spell. Non-significantly. Sig, nif, cantly. Is that right? Did I spell that right? Word doesn't like it.
So you have a space. You need a space. chapter, non.
No, it's one word. Not significantly would be two words. I think Word just doesn't like that it's not, that it doesn't recognize it. Non-significantly is a word. You know how I fix that? Right click, add to dictionary. Done. Now it understands. Pro tip. Okay, how we doing? Ish? Okay, so big picture, square things makes a U. What if you have a relationship between variables that you don't want a U for, but you want to convey that more stops being helpful at some point? That's where log transforming can give you a decent approximation to that. So I want to show you a picture of what that would look like. I don't have an example, but you can do this on your own if you want. So what I have here is time, again, as a predictor. And if you look at the bottom plots first, the x-axis is natural log transform time. And the black line describes what would happen if you fit a linear slope to that log transform predictor variable. The slope is linear between log transform predictor and the outcome. That same positive linear slope, if you exponentiate the predictor, so unlog it back to its original scale, it creates that black line right there. So this creates a curve where more helps, but only up to a point, potentially. Or in this case, less is better, but only up to a point. And you can take those log transform variables and square them to create something that looks even more like it asymptotes or less. So the plots of the top two give you what the resulting curve would be with respect to the original predictor. The bottom two describe then what it would look like for the log transform predictor. So this is much easier than fitting an actual exponential model. This is a mimic of it, so to speak. So that's something that you can easily add to your toolbox by log transforming your predictor. So, thoughts, questions? All right, no. So let's go back to education. So in example 3, I had a model in which I predicted income as a linear function of education. So conceptually, does that make any sense? Do you get the same bang for your buck, so to speak, for every year of education? No. No. If I go from 2nd grade all the way up to 11th grade, but I drop out, I'm a high school dropout. Whether I dropped out in 2nd grade or 11th grade is irrelevant. Right? Same thing with master's and dissertation work, right? If you get all the way through all your classes and all the way through comps and all the way into your dissertation proposal, if you never turn that thing in, you don't have a PhD, right? You still have the degree that you were admitted with. So there is very much a discrete, stepwise effect of education because the benefit doesn't kick in until you hit the desired level. So years is somewhat of a poor proxy for this idea, but it's all I've got. But you can see, just by looking at the mean level of income for each distinct year of education in the data set, this kind of stepwise approach. So people who have between 2 years of education up to 11, there's not much difference in their income. Oddly, the people who have the fewest look a little bit higher, but there's not very many of them, as you can see for the range of the standard error bars around it. If you graduate high school, you get a bump. From there, if you have more education, you get more, but it looks like it's a sort of a discrete function as well, where 12 to 15 doesn't get you much, 15 to 16 gets you more, because that would probably correspond to a bachelor's degree. Hopefully 15 up to 18, yay masters, and then after that, more education is bad for you. So hopefully none of us are in this business to get rich. I would say you have made a serious error in judgment if that was your intention of getting a PhD. Although we can live comfortably, hopefully, as an objective. But rich is maybe not on the menu. So I want to show you how to operationalize this kind of idea that the effect of more for having education depends on where you are within the scale of education. So what we're going to do is carve it up into pieces. We're going to fit, to be consistent with this example, one slope for the effect of education from 2 to 11 years, which I would hypothesize is probably going to be a flat slope, doesn't matter. Another slope that captures the jump from 11 to 12, which it looks like that should matter. And a third slope that captures a linear effect of years of education from that point. And I'm doing that because this model is already sufficiently complicated. Probably should have had something nonlinear at the end, but I leave that for those of you who want to play with the data on your own. So that's what we're doing conceptually. Does that part make sense, the setup? Okay, now how to do it is the tricky part. And of course, you will get a chance to practice this in homework 4, albeit it will be a simplified version with only 2 slopes instead of 3. But here's what we're going to do. We're going to create 3 new predictors that capture the range of education for which we want distinct slopes. 3 ranges, 3 predictors. I have to set one of the years of education as the model 0 point to create an intercept. So I have chosen to do that at grade 11, which is why it's highlighted in yellow here. So for the 3 new predictor variables that I'm going to be creating, I'm going to set each of them equal to 0 if a subject has grade 11. Relative to that, the first predictor variable in this column here, less HS, standing for less than high school, is going to capture the effect of education prior to 11th grade. So if I called 11th grade my 0, then for somebody who only has 10th grade education, that has to be a -1. Now I know that looks kind of strange, but it's because of how I've defined 0. 10th grade is 1 less. 9th grade is 2 less. So I would want to write a function that subtracts 11 from every value. That's what's going to have to happen. But because I want this slope to only capture the effect of education prior to 11th grade, I zero it out all the rest of the way down. So it stops after 11th grade. It does not index changes in education anymore. Second column. The second column is going to index the bump that you get for graduating high school. So I've called this variable grad HS, and it simply changes from 0 to 1 when you move from 11 to 12. I have zeroed it out before I hit 11, and I have 1'd it out after. Is that a saying? I 1'd it out? I think it works. Because it's not zeroed out, it's 1'd out. Because if I had zeroed it out instead, I would have put them back down. So I want them to be able to maintain a bump across all of these higher levels of education because they at least graduated high school. And so then the third variable picks up where the last one left off and says, okay, so if you have more than 12 years of education, so the slope for people who have graduated high school, what is the effect of each additional year? And so then this one is created with the baseline of 12 to index subsequent changes in education. And it's zeroed out ahead of time when it's not relevant. So these 3 variables together describe the overall possible range of education values. They do so in 3 distinct segments. So the term for this, I call these piecewise models. You might hear these as linear splines as another term for this. These models are very useful if you have a theoretical or practical reason where you want the break to be. So like in this case, I am deciding a priori how many distinct regions I'm carving this predictor up into and where the breakpoints are. I am deciding that. These types of models as fit in this software require you to make that decision. There are other models in the world though that try to find the breakpoints for you. And the term that you would look for if you're interested in that is latent splines, where latent means something that has to get estimated by the data, where the breakpoints are. Okay. How are we doing? Ish? Fayaz, you hanging in there? You're slumping in the chair. It's like, there you go. Get some caffeine. And Emmy's like, ah, with the emoji. You're hanging in there, Emmy?
Yeah.
Awesome.
This is more the ish situation.
You need an ish icon, I know. Ish. Big picture, we don't think that a linear slope that says you get the same benefit to your income for every additional year is reasonable. So we're carving education up into 3 distinct variables and fitting a linear slope for each of the distinct sections. That overall will allow a non-linear relationship between education and income. Here's the code that generated this table. So in each program, the first step is to make 3 blank columns, same as usual. So here's the Sas code that goes with this, and I'll show the Stata code in just a second. So I am using 2 conditional statements here. If education, LT stands for less than, you can use the symbol or you can say LT, 12, then do. So if I'm talking about cases that have less than 12 years of education, then I want to make this first column as education minus 11. The second column gets zeros, and the third column gets zeros. So this first line of if education less than 12 is filling out the first 3 rows of this table. The second line then covers the rest of the rows. If education GE, can you guess what that stands for? Not a refrigerator. Any guesses? GE?
Greater?
Or?
The same?
Yeah, greater than or
Equals?
equal to, yeah. So I have less than and then I have greater than or equal to. So I've covered all scenarios here. So inclusive of 12 and greater, so in other words, the rest of the rows in this table, the first variable is a 0. The second variable is a 1 because they would have graduated high school in each case. And the third variable is how much past high school they have. So education minus 12 picks up where graduated high school left off. And then those are the 3 new columns that go into the model. Stata code has more lines to it, but does the same thing. So I have the first 3 statements here correspond to the less than line in Sas. So if education is less than 12, generate the first column as education minus 11, 0 out the second column, 0 out the third. Then if education is greater than or equal to 12, 0 out the first column, 1 out the second column, and then this is education minus 12. And then the 3 new predictors go into the model. Okay. So then we get results, which I think we can probably save till next time. Would that be okay with you? Yeah, we're hitting that point in the day. I feel it, you feel it. I'm not shirking my academic responsibilities if I let you out 5 minutes early, right? That's cool. Yeah. Okay, Jen, since you insisted. Yeah.
I mean, you have tenure already, so does it really matter?
You make a good point.
Oh, are we getting rid of that in this state? So maybe it does, you know?
Yeah, people are afraid of that. I don't know that it will ever stick. But that remains to be seen. But yeah, I do have tenure, so who cares? We're leaving early. 4 whole minutes. All right, any questions before we leave early? All right, then it is Thursday, not garbage day, which means have a good weekend, do your formative assessment, and let me know if you need anything. All right? All right, have a good one.
Dr. Hoffman, can I ask you a quick question?
Yes.